Hi everybody. Today I'm going to be talking to you about hardened concrete tests, and this presentation is by Samantha Suero. So first thing I'm going to be covering, well, not first thing. This is like a run through of all the different types that we're going to be covering today. So we're going to talk about there's like five major types. There could be more, but from what I understand, it's mainly these five. We're going to be covering strength testing, volume changes in the concrete, freeze-thaw testing, absorption/permeability testing, and the microstructural characterization. And that's kind of like just like what it's made up of, like the little aggregates and all the stuff that you can see and how its structure, which we won't cover too much on that one because that's actually more fresh concrete. But moving on, let's start with strength testing. So there are a lot of different ways to test the strength of concrete. I specifically am only going to be covering 8 of them because I these are the ones I found the most information on or found most common. And to start off with, we're going to go to the most common method of strength testing, which is using the field cured cylinders. You've probably heard us talk about this in class before, and it's basically whenever you have a cylinder out on the field, try to keep it in like the same conditions as the concrete you're working with, and you let it cure. You're going to send that to a lab. It'll all of the strength testing for that will be done off-site in that lab. So this method, it's non-destructive, which is a pro for it, but it's not really the most effective or the most easy method. But a lot of people still use it because it's like, oh, if it ain't broke, don't fix it, or a lot of people say it's just the way it's always been done. But it doesn't mean it's the fastest or most accurate. However, it's definitely a very viable and common method to test strength. The next method that we have for strength testing is the rebound hammer or Schmidt hammer test. And what this is it's like a hammer mechanism that is quite literally going to just it's going to have a plunger on it that's going to impact the concrete, and they take that rebound distance from the hammer to the surface of the concrete, and they give it a value from like 10 to 100, and then that value correlates it on a level of strength. It's actually, now that I look at my slides, that's supposed to be 10 to 100, not 1 to 10. Um, so this method, it's pretty relatively easy to do. It can be done on site, and like I said earlier, it's non-destructive, so that makes it a pretty good method to use. I'd say its main con is that you do have to pre-calibrate it. It's not something that's already like you just bring it on and set it to go. You have to give it like a baseline to work off of. So the next thing that we're going to talk about is penetration resistance test. So what this is you're going to quite literally just penetrate the concrete with like a little pin or probe into the surface, and the way that they get the strength from that is they're going to figure out how much force it took to like penetrate it, the depth of the hole, and they're just going to correlate that to the concrete strength. Now, the benefits of this is that it is also like a relatively easy thing to do. It can be done on the site, doesn't have to go off site. And a big con though is that the data that you're going to get from this can be really affected by the surface conditions of the concrete. Because I'm sure if it's got like a brittle like shell or maybe like something like on it that could mess up the pin penetrating it, then that could definitely affect your data. Next method I'm going to go into is the ultrasonic pulse velocity test. So this one is a little more high tech. And what it is you're going to have a pulse of energy go through the slab, and they kind of measure the strength based off how easily that energy or like frequency can go through your concrete slab. And it'll actually give you a few bits of data. It'll give you its like elasticity, its resistance to stress, the density, and then they use that to correlate it to strength. So this one, also non-destructive, which is always good. And another cool thing about this is that it can actually detect flaws in your concrete. Like if you have cracks or honeycombing inside that you might not be able to see, it can actually detect that, which is a pretty good thing to know about. And the con of it, though, is that it is another thing that its data can be highly influenced by other factors. So, like the moisture in the concrete or the aggregates that you have in it or whatever reinforcing that you have inside the concrete can really affect the data. And so it might not always be a good, accurate testing method if you have a lot of, say, reinforcement inside your concrete. The next one is the pull-out test. So this one is basically you're going to have a metal rod that is cast in place in the concrete, and they're quite literally going to pull that rod out. And that's usually going to pull a good chunk of concrete out with it. And then they look at the shape, and it's usually got like a cone shape whenever it comes out. And so they look at that shape, they look at the force required to pull it out, and they correlate that to your concrete's compressive strength. So obviously this one is very destructive, so that's a big con, but it's easier to use. It can be done on site, and you can do this on like old or new construction. So like some of these methods can only be done on like brand new concrete versus others you can do on like an older construction that's been around for a bit. And next up, we're going to be covering the, oh, did I repeat one? It seems I repeated the pull-out test twice, so we won't cover that. The next is the drilled core. So drilled core test is going to be when you have a core, like just quite literally just like a core of concrete that you drill out from a slab. And then you're going to compress this in like a hydraulic press or something of that sort and see how much force it can withstand, and you'll get your strength based off that. This one is going to be a lot more accurate than your field cured cylinders, but this is going to have to be taken off site, and it's very destructive because you're literally pulling a core out. So the other one is wireless maturity sensors. These are more high tech, and you're going to have these sensors placed like around your reinforcing or wherever you're going to be, like your formwork, wherever you're pouring your concrete. You're going to put these in before you pour the concrete. And this actually does connect a bit more to fresh concrete. So I won't cover it too much, but we talked about that temperature curve whenever concrete is setting, and it measures that to find the strength when it's set. And next one we're going to talk about is the cast in place cylinders. It sounds a lot like pretty similar to that first one, the site cured cylinders, or field cured cylinders, but these are different. These ones are actually cylinders that are placed in the location that you're pouring your concrete. They're not just on the field. They are in the location, and then you have to remove them and do the same test. So like you're gonna get a lot more accurate data than with field cured because it's like the actual same concrete. But a big con of this is the destructiveness. So here I have like a table that just kind of sums up a little bit about each of the types of methods that I think it's pretty cool to look at if you just want to pause and take a look at this for a quick summary of what I just covered. So next up is volume change testing. So volume change testing is when well, first off, there's two things you have to test for to determine the concrete's volume change. And you need to find the coefficient of thermal expansion, which is going to depend on temperature, the internal structure of concrete, and the moisture content in concrete. And the reason that this is important is because if you have CTE, or we're going to call it CTE, determinations, they predict like thermally induced expansion and I can't speak, contraction movements in concrete pavement. So this CTE value will help you predict how much it's going to contract and expand. And then it helps you figure out what mixes you're gonna make to like maximize like service life of the concrete, which that's more fresh, so I won't cover that. And then next up we have you need to know the restraint, or this is actually a type of test, and it is the restrained drying shrinkage test ring. So this type of test is when you pour in wet concrete, you let it set and harden, and then you see how much pressure it exerts on like this outer wall that it's got going on, and that value will like it gives you like a value of how much it is actually expanding. So, and it can give you the susceptibility to early cracking, whether that be due to drying shrinkage, autogenous shrinkage, or heat of hydration. So, what are these values? Drying shrinkage is going to be when the concrete contracts due to a loss of water, while autogenous shrinkage is going to be a more uniform like reduction of moisture in the concrete because the cement becomes hydrated. And the last one is heat of hydration, which is basically just whenever it is curing, a lot of heat is produced off concrete. I mean, it can burn you, so that's another value you need. So next up is going to be the freeze-thaw testing. So freeze-thaw test measures the resistance of concrete to deterioration through repeated cycles of freezing and thawing water, and that is exactly how it sounds. You freeze it and you thaw it and you see how it goes. But I will say that this method is going to be a lot longer and complex, so it's not going to be something you're going to just do real quick and get the results. It's going to take, it has to be a lot of cycles of this freezing and thawing. And you use this to evaluate concrete mixtures before you actually use it. So, like, this isn't, I mean, it is a long method, but it's not something you're doing after you've already built your structure. This is something you would be doing before you've built your structure to see whether or not your concrete's going to hold up over time, and then decide if you need to change whatever mixture you have going on in your concrete to make it better, or keep it the same if it's good. And to just like put it in perspective how it can really affect it, water does expand by about 9% as it becomes ice, and so as you can imagine, that will affect your concrete. And usually, freeze thaw, the effect of it is you'll see this thing called scaling, which is when the concrete looks like it's flaking off, kind of like dead skin. And that's usually how you'll see like the freeze thaw testing. Next up is absorption or permeability testing. That's when you're testing the specific gravity, absorption, and the air voids. But I put air voids in microstructural because that's how the NAP classifies it. So we'll cover that in the next slide. But the way you'll test this is you'll subject concrete to a hydrostatic pressure, and then you're going to measure how much water that can actually percolate through at a certain time to find the coefficient of permeability. And this will determine how much water can like seep into your concrete over time. And these tests are very important for any concrete that'll be in contact with water. Like if it's going to be a marine dock or anywhere near water. So you can imagine that here in Florida, these are a very important test to conduct because you want to know how much water is going to get through your concrete and then deteriorate that over time, whether that be from severe climate or leaching or anything like that from just the water exposure. So lastly, we have the microstructural characterization. So this is it's quite literally the microscopical detailing of the concrete components from its macrostructure. So that's just fancy words to say like what are the bits and pieces inside the concrete. And I'm only going to specifically cover air voids because a lot of the other tests have to do with before when it is a fresh concrete, such as like the ingredients being dispersed wrong or the mixing being wrong or distribution, etc. But I'll leave that up to the fresh concrete. So air void test, that is going to be done when you have your hardened concrete. So the way you test for air voids is you're going to compact the concrete like as hard as you just compact it, and then you're going to compare that bulk density to a theoretical maximum density, and then you're going to assume that the weight difference is air voids because air voids are like very small, like air doesn't weigh much, so it's kind of hard to put a value on it, but that's how they do it. And I will say it is a time consuming and destructive process because you do have to take out a core and then compact that core and do these tests. And below I provided the formula to find your percent air voids, which is basically just the formula version of what the words say. So there are other methods. You can also do these tests using a nuclear density gauge or a or that's a specific example, but or an electrical density gauge. And the nuclear one will use radioactive sources to identify the concrete's thickness, density, and makeup of like the concrete. And then the electrical one is basically just the non-nuclear alternative for the first one, and it determines the physical properties of the like compacted oh, sorry, I never clicked the slide. These are the two, and it kind of it uses like frequencies to figure out percent error voids. It's a bit complicated, but there are alternate methods, but I'm sure that they're a lot more expensive and maybe not as accessible. But that is it. Here I have a list of my sources.